moving to the next topic of the course. So, most of you would have heard this term. So, it is not a new topic, except that the flavor in which you would see things, the flavor in which we would quantify them will be completely different from what you would have learned earlier. And for simplicity purposes, there are several aspects of quantification which we will cover them in this class. We will look at several things. One is we will start looking at definitions of radiation. We'll look at various definitions associated with radiation. We will look at what is the, how to quantify, that is, how to find the heat transfer rate. For various cases, radiation could be emission, absorption, transmission, etc. So, we will look at how to quantify it for various processes, various radiation processes, and then we will look at black body radiation. We will look at what happens when there is a black body and how to quantify emission, absorption, etc. from a black body. And then we will look at so there is a special law for radiation which captures the relationship between certain properties of radiation, and that is what is called Kirchhoff's law, and we will actually look at that. And then so while doing this, we will also cover what is called the gray surfaces. What is the definition of gray surface and how to quantify them, we will look at that. And then the fifth aspect is we will look at radiation exchange. So, supposing if there are multiple objects, then how would you exchange, how do these objects exchange radiation between themselves, etc. And while doing that, we will also look at we look at something called view/geometric factor, because the radiation is now going to depend upon the orientation of these different objects. So, one needs to find out what is the effect of the orientation, or that is what is generally called as view factor or geometric factor. So, we look at how to calculate the view factor and geometric factor for various kinds of systems. So, that is what we will sort of do in the next 8 lectures. After we finish this, there will be several examples. That we will go through, and it will be somewhere around anywhere between 7 to 8 lectures is what I would estimate for this topic. Okay. Alright. So, what is radiation? So, radiation is any matter emits energy simply by the virtue of having a finite temperature. So, this is the most general definition. So, any matter, in fact, we can even qualify it better by saying emits/absorbs, etc. We will worry about transmission later. So, in general, emit/absorb energy simply by the virtue of it having a finite temperature. Okay. The fact that it has a certain temperature, it has certain energy stored in it, and therefore, it is exchanging radiation. In fact, every object in this room is emitting radiation. Blackboard, this bench, etc. Everything is emitting radiation. And it's not just that it is emitting radiation, it is actually exchanging radiation with itself, with all the object which is present here. So therefore, exchanging emission, exchanging radiation it's a ubiquitous process. Exchanging radiation is ubiquitous, it's found everywhere, it's found in all objects, our hands, everything is radiating. So out of curiosity, so there was a place where I had an access to infrared camera. How many of you have heard about infrared camera? Oh, not bad, okay. So if you place your hand in front of the infrared camera and you measure the profile that you will get, measure the image. So the image that you get from an infrared camera reflects the local temperature of that surface that you are looking at. Okay. So if you keep your hand in front of the infrared camera, you will be surprised to see that all locations they have different temperature. So you don't have a uniform temperature profile even in your palm. There is a definite temperature profile. In fact, if you get an access to infrared camera in some of the labs, there are infrared cameras in this institute. So if you get an access to some of them, it's not a bad idea to just sort of get an idea of how the temperature profile looks like in your palm or hand, etc. So really, the temperature profile is quite different than, and it's not uniform. And so if I'm actually putting my hand, there is a heat exchange between different part of my hand, one hand to the other hand, because the temperature is different. So exchanging radiation is actually quite a ubiquitous process. It occurs across all matters, all objects, etc. Okay. So incidentally, there is a, I don't know how many of you read newspaper yesterday. So there's this new type of bulb that's going to come out. It's called a liquid cooled LED. How many of you read the newspaper yesterday and today? I think it came out yesterday, the newspaper. Nobody? Nobody? So it's called the liquid cooled LED. If you have not seen, you should go and see it today. It's actually one of the direct applications of what we are actually studying in this course. You know, LED lights, most of these incandescent lamps and LED lights, the problem is it emits a lot of heat. Particularly in LED light, the LED itself does not emit heat, but there is a panel which supplies electricity, etc., and controls the glowing of LED. So that emits a lot of heat. So the life of an LED lamp is actually dictated by how one can control heat transfer, how one can keep the chip which is present below the LED under normal temperature. So if one is able to keep it at a normal temperature, then you can actually have a longer life for LED. So these liquid cooled, it's going to be the next generation bulbs. It can glow for 25,000 hours. So that's remarkable. We have never seen any bulb which can actually glow for that long. None of the bulbs that we know. So it's really remarkable, and if it really works, it's going to completely change the paradigm of conservation of electricity. And in fact, it's supposed to be very efficient, and it takes about 80% lesser energy than the normal incandescent lamps that we have here. So if this works, it's really a great technology. Anyway, so it has a lot of implications, and it's a direct application of some of the things that we are studying in this class. So they have worked out what should be the optimum amount of heat transfer that should occur between the LED panel and the liquid. There's a small amount of viscous liquid which is actually circulating inside, and they have made a precise calculation of how much should be the exact heat transfer and what should be the volume of the viscous fluid, etc. So it's an interesting property, and in fact it's one of the direct applications of what we are actually going through in this course. Anyway, after this digression, so let's go back to what we are looking at. So the mechanism of radiation. So let us look at what is the mechanism of radiation. Okay. So as he rightly pointed out, what happens is because there is a certain object which is at certain temperature, so there are these electrons which are actually emitted from the surface, and so there are two theories which are actually available to explain the mechanism of radiation. So one is called the quantum theory, and the other one is called the wave theory. So the quantum theory, again it's a postulation. It's believed that the object, because of its certain temperature, it emits quanta or photons, and these photons they travel, and when they hit the other object they leave the energy, and that's how the energy is being transmitted from one object to another. The other theory is that these are electromagnetic waves, because of the temperature of that object it emits electromagnetic waves, and these electromagnetic waves are intercepted by the receiving object, and that causes exchange of energy between two objects. So these are the two theories that are actually existing. So we are not going to debate about which is right and which is wrong, that's the problem of the physicist, but it wouldn't matter to us, because as long as we know either of these theories is right, we should be able to quantify the process, and we are going to see that in a short while. Okay. Alright, so when we looked at conduction, we said that heat transfer via conduction, it occurs through a cross sectional area, right. So similarly, we need to know what is the geometry at which the radiation is going to occur. So the first question is it a surface area or a volumetric phenomena? So the first question we need to answer is it a surface area or a volumetric phenomenon? So remember, when we discussed conduction, we said that the thermal diffusion occurs across the cross section, while the capacity to store heat is a volumetric process. So what about radiation? Is it a surface area or a volumetric process? So he says that radiation can occur only from surfaces, and so it's a surface area process. What's your thought? You said it's volume process. Okay, so in the class we have got two thoughts. One is that radiation emitted by surface so it has to be a surface area process, and the second thought we have got is radiation emitted by all the molecules, so it has to be a volumetric process. So which one is right? So the correct answer is both are right. So you would not intuit as to why both are right, so that's what we are going to explain in the next few minutes. So in fact, any material that you take, so the second suggestion is always right. The radiation is emitted by all the molecules which is present in the matter that you are considering. So now supposing we have solid, okay, or liquid matter, okay, so let's say it's a solid. All the particles which is present in the solid, in principle they are going to emit radiation because they are all maintained at a certain temperature. But what happens is, the molecules which are present at the interior location, anywhere inside, every radiation that is emitted by one molecule is also going to be absorbed by the molecules which are surrounding them, right. So therefore, there is whatever is emitted by the molecules which are present inside, they are going to be constantly emitting and absorbing radiation. So therefore, all the radiation that actually comes out of this object are essentially from the molecules which are located close to the surface. So I will give you in a short while what is the length scale. So all the molecules which are actually located close to the surface are the ones which are actually resulting in the radiation which is emitted out of this object. And in principle, what is believed is that the molecules present about 1 micrometer below the surface is responsible from that surface. Now note that this is true for solids and liquids. It is not true for gaseous systems. So remember that gases also emit radiation. So the radiation is emitted by all the systems. So we observed that radiation is emitted by all forms of matter. So when it comes to gases, it is slightly different. Because the density is very small, right? Density of gases is very, very low. And so supposing if there is a gas which is placed in a container, now you have molecules which are actually dispersed in this medium, and as we observed, every molecule in principle can emit radiation, and because the density is not sufficiently enough, the radiation emitted by one molecule is not necessarily completely absorbed by the molecules which are present around them. Therefore, in gases it is a volumetric process, it's a volumetric phenomenon, while in solids or liquids it is a surface phenomenon. So most part of the discussion we are actually going to look at the surface area phenomenon. We are going to characterize radiation, quantify, etc., and then apply some of these principles to the volumetric phenomenon towards the end of the radiation topic. Okay. So whether we believe in the quantum theory or the wave theory, we can always characterize radiation. Radiation is always associated with a certain wavelength and frequency. Okay, doesn't matter whichever theory we believe, it's always associated with a certain wavelength and certain frequency, and so we can always say that lambda equal to c by nu. Okay, where c is the speed of light under vacuum conditions, approximately 3 into 10 power 8 meters per second. So that's the speed of light. It's 2.998 something. So approximately it's about 3 into 10 power 8 meters per second. So any radiation is always associated with the wavelength and its frequency. So if we know the wavelength, we know what the frequency is going to be. So therefore we are going to talk a lot about the wavelength of the emission. So supposing if I take a monochromatic radiation, okay. So when I say monochromatic, which means that the radiation is emitted at a fixed wavelength, right? A single color, which means it's a fixed wavelength. So if I look at the monochromatic radiation intensity, versus lambda, okay. So at a fixed wavelength, what is the intensity of the radiation emitted by a certain object in that wavelength. Okay. So then the typical profile is something like this. It doesn't matter what these numbers are, we will see that later. So this property of radiation of an object to be dependent upon the wavelength is what is called as spectral. Really the wave comes from, the word comes from the idea that there is a spectrum for radiation, and so this is called the spectral property. The fact that it depends on the wavelength of the emission is called the spectral property. So this is the first important dependence. Then the second one is the directional dependence. The radiation is also dependent on the direction at which the emission is occurring. So in principle, as a cartoon, supposing I have a point object here which is emitting radiation. So the emission in this direction could be, so the length of the arrow, if I say that indicates or denotes the intensity of the radiation. So the radiation intensity is different in different directions. So that's what it means by saying it has directional dependence, and theta is counted from this angle, going from 0 to pi. Now when it is a surface phenomenon, the emission is only in the one direction, right? So if there is an object here, if I want to characterize the emission from that surface, it's really emission is occurring only in the upper plane of this surface, that is the upper hemisphere of that surface. Note that it's a three-dimensional process, so it's going to depend on theta. It's also going to be dependent on the phi angle, right? So if you imagine a sphere, there are two angles to the sphere. One is generally called as theta. So in any sphere, you have three coordinates: r, theta, and phi. So in principle, the radiation, if I put a hemisphere on top of this, so the radiation that is emitted by that surface is in principle dependent on both theta and phi. So theta is, if I say this is the theta direction, then phi is in the direction outside the board and inside the board. So note that it's actually going inside the board, it's a circle inside the board, okay. So the radiation is now going to be a function of both theta and phi. So these are two important properties of radiation which needs to be accounted for if you want to quantify the amount of heat transport because of radiation. So if it is a black body with a fixed radiation, it will be at a single peak. If it is a grey surface, there will be a flat peak. So we are looking at solids. We will look at gases later. So note that gases can in principle emit in all the directions. So the question is whether it is continuous or discrete. Now the discrete nature, we are going to see that sometime down the lecture, one of the lectures we will see. So when you have grey surfaces, particularly hydrogen is actually a grey surface, it's a grey molecule, it's not a black body radiation. So when you have grey surfaces, it's not that the spectrum is continuous, you will have a discontinuous spectrum. We will see that, we will see that shortly. Mostly 3-4 lectures down the line we will see, yes. Oh, sure, because see, supposing my object is here, okay, supposing my object is present here. Now the emission from this surface is a strong function of the roughness of the surface. So you will never get a smooth surface. Even at the microscopic level, you cannot have a smooth surface. So there will be small crevices around, and therefore the emission in different directions is going to be different.